Hey everybody, Paul here for this week's videos. Sorry if you have watched the other one and you found that I didn't have sound. I'm trying to fix that right now. This week we're going to go back to the first question we looked at that started us off on this graph theory course, and it was the idea of you have this map of the bridges of Königsberg, and you're trying to see if you can find a route that goes over each bridge in the city of Königsberg exactly once. And what we found was it doesn't really matter where you start or what you do, you're always going to end up stranding at least one bridge, right? You can start over at C and you can go like this, and you're no matter what, you're always going to end up stranding a bridge. And again, try it yourself if you want, but you can't do it. And this question is kind of what inspired Euler, the guy who invented graph theory, right? To turn this bridge, this map, into a graph. So notice that this graph is isomorphic to that map. It's the same thing. And you'll find that no matter what kind of route you take here, or I guess we would call it a path now, you'll always strand at least one edge. And there's a name for what we're trying to do here. Finding a route that goes over each bridge, or in graph theory terms, goes over each edge exactly once, and that's called an Eulerian path. So an Eulerian path is a path that uses every edge exactly once, and that means no edges are left out and you don't double up on any edges, right? And just a reminder of a path, that's a series of connected edges where edges are not repeated. So this question here is about finding an Eulerian path for this, and it turns out it's not possible. And just to play a little game, I'm going to list the degrees here. So this vertex has a degree of 3, 3, 3, and 5. So we'll say that a set of 3, 3, 3, 5, there's no Eulerian path. Okay? Didn't work. Now, what's funny is, like, I actually remember being a kid, probably like 8 years old, and trying to do this for this graph on the board. I didn't call it a graph, I just called it a picture, right? But I remember being a kid and trying to trace this image with a single pencil without picking it up, and I couldn't do it. And I would try and try and try over and over again, you know, in the way that kids are, oh, maybe if I do that, but I always ended up not being able to do at least one edge, if not two edges, right? And it turns out that for this graph, you also cannot find an Eulerian path. And just to look at the degrees, we have a 3, a 3, a 3, a 3, and a 4. So for a degree set of 3, 3, 3, 3, 4, there's no Eulerian path. Okay? But then I realized that if you take this image and you change it, you could actually find a way to draw it without lifting up your pencil. And here are two versions of that same graph. Notice on the one on the left, we kind of deleted this edge right there. And the one on the right, we added in an edge here. We doubled up on this edge kind of, right? And this one, I'll give you a minute, like pause the video, see if you can find an Eulerian path, okay? Great, you've unpaused it. Did you find one? Well, you can actually. There are ways to find Eulerian paths on this graph. Now you got to be careful. If you start right here, you'll find that it doesn't work, right? And if you start on the top ones also, you'll find that it doesn't work. But if you start on one of the bottom two vertices, you can trace this out and cover every edge. So here I'll do it like this. And notice I'm using the edges more than once. I'm just not using the, I'm using the vertices multiple times, but not the edges. Now what's the degree of this? So that's a 2 and a 2 and a 3 and a 3 and a 4. And so we get a degree set of 4, 2, 2, 3, 3. And I'm writing it a little bit weird, and you'll see why in a second. Right? So that's our degree set. And likewise for this one on the right. Pause the video, try it out. I think you can find that you can find an Eulerian path, okay? Same thing as last time. I'm going to make sure to start on one of these bottom corners. And then, as long as I'm not too careless, we get our path, right? And likewise, I could start in this one, and I could go like that, and around and up, over, and there you go, right? And so it turns out that for both of these graphs, there is an Eulerian path, right? There is for both of these. And just look at the degrees here. We have a 4 and a 4 and a 4 and a 3 and a 3. And so our degree set would be 4, 4, 4, 3, 3. Now, Euler looked at these and he said, well, why can you do this Königsberg bridge problem for some and not others? And he did what mathematicians do. He found a pattern. If you notice, for both of these graphs, there are only 2 odd vertices. And in the paths that we found, you have to start at one of the odd vertices and end at the other. So we started here and we ended here, right? And if you go up to this one where it didn't work, there are more than 2 odd vertices. There's 4. And in this one as well, there were 4 odd vertices. And Euler came to a conclusion, and it's kind of amazing because it's really simple. In order to have an Eulerian path in a graph, you only have to have one thing be true. You have to have exactly 2 vertices with odd degrees. So here's the theorem he came up with, right? Theorem. A graph will have an Eulerian path if it has exactly 2 vertices with odd degrees. That kind of implies every other vertex has even degrees. Now the cool thing is this works both ways. So if you look at a graph and it has 2 vertices with odd degrees, it will have an Eulerian path. And if someone tells you that a graph has an Eulerian path, you will know that it has 2 odd vertices, right? And I'll give you like a very brief theorem, like a very brief proof, right? So we have our graph, and I'm only going to draw the odd vertices, and all the other vertices I'm going to say are somewhere in here, right? So this is all the even vertices, okay? Now the idea is that we're going to start at this odd vertex, we're going to go into the even ones, and then we're going to bounce around inside these even ones, going in and out, in and out. So every vertex, we're always going to go in and out. So that's going to use up 2 of the edges. And then we'll come back and we'll go in and out. That uses up 2. And every time we're using up 2 edges. And so because these are all even vertices, we can always go in and come back out. And we might even go back into this one and come back out, and that uses 2. But we have this starting odd one. And eventually, we'll make it maybe in and out with the 2. And we end up going back into this one with our odd one. And we're done. We can use every vertex inside this box because they all have even degrees. So we can bop in and out, in and out, in and out. We're starting here. We start at this one. And we're ending here. That's not super rigorous, but that's the idea. And that's what you're going to play around with this week for the first assignment, is finding Eulerian paths or saying whether Eulerian paths exist. And again, it just comes down to the number of odd degrees. You need to have exactly 2 to have an Eulerian path, okay? Hope that made sense. I'm here for questions during class and office hours. Take care, everybody.